Hello everyone, and welcome to the third session of this lecture series entitled Excel in Structural Engineering. We will continue learning how to create an Excel template to be used for the flexural analysis of rectangular singly reinforced concrete beam cross sections. In the previous session, we assigned names to all of our input parameters. Today, we will assign names to all of our output parameters. Eventually, all of these assigned names will be used to define our equations and formulas that will produce the actual output parameters. Let's revise the input parameters and their assigned names so far. This one has been assigned the name B, small letter B, small letter H, Fy, FCP, DBB, DBT, NOBB, NOBT, cover, and DS. These were our input parameters and their assigned names. Now we will assign names to our output parameters. Please pay attention that the names assigned to the output parameters are completely different from the equations and formulas that will be assigned to calculate these parameters as well. At this particular stage, we are only assigning names to the destinations or addresses in the output parameter zone. Let's start. Click on the address that you want to assign a name to, and then here you can assign the name required, ASB. The next one will have the name AST, then AS, YB, YT, Y bar, D, DT, row underscore S, B underscore min for minimum, B minimum, AS underscore minimum, beta underscore 1, the correlation coefficient between C and A, small letter A. Now here, pay attention. In the previous session, I've mentioned that you cannot use either the small letter or capital letter C because it is reserved for the word column, and therefore we cannot just assign the letter C here. So instead, I'm gonna define a name for this variable, and I'm gonna call it C of A, which stands for the parameter C that can be obtained from the parameter A. You can give it any name you want, but I'm referring here to the fact that C, which is the depth to the neutral axis, and it can be obtained from the depth of the Whitney rectangular stress distribution A. That's why I'm just calling it C of A. For the next parameter, I'm going to assign the name CDT. For the lower limit of C over dt according to the ACI code, I'm just going to copy this name and assign it to this address. Same thing here. This is the lower limit of C over dt. This is epsilon t. Epsilon y is the yield strain, which is actually the lower limit for epsilon t values according to the ACI code. This here is the upper limit for epsilon t. Remember, you can use either C over dt or epsilon t in order to determine the section ductility, determine whether the section is in the tension, transition, or compression controlled zones. This parameter will be given the name phi. This one here is Mn, the nominal moment or the nominal strength, and the last one here will be phi underscore Mn, which is the design strength, or phi times Mn. For the last merged cell here, I will give it the name S type, standing for section type. Here we will display whether the section is adequate or inadequate. Double enter, and there you go. Let's go through them again. This one is ASB, AST, total area of reinforcement, YB, YT, Y bar, D, DT, reinforcement ratio, B minimum, AS minimum, beta 1, parameter A, parameter C, which is C of A. Remember, you cannot use the letter C, whether a small letter or capital letter. C over dt and its limits, lower limit and upper limit. Epsilon t and its limit, this is the lower limit, which is the yield strain, and this here is the upper limit. This one here is phi. This one is the nominal strength, and this one here is the design strength, and the last address here will show whether the section is adequate or inadequate. By this we have assigned names to all of my input parameters and my output parameters. The next stage is to insert the equations and formulas that will calculate each and every one of the output parameters. I have prepared a table that presents all of the equations that we will need for this Excel template to be fully functional and capable of calculating the output parameters. We will go through these equations one by one to understand the syntax and logic applied to develop them. This is a very important step because we are condensing our structural engineering knowledge and pouring the results into cells that will perform all of the required calculations. Not just that, but these cells in the Excel template will then determine whether the section is adequate or not. If adequate, the Excel template will present the flexural design strength of the section, and if not, the Excel template will indicate that the section is inadequate and the design strength will not be provided. In the table shown on the screen, on the left side we have the equations required to calculate the output parameters, and on the right side we have the same equations but written in Excel language. So for example, if we look at the first parameter, which is the area of steel in the layer farthest from the neutral axis, this output parameter can be calculated using the following equation. Between parentheses we have the area of a single bar in the layer farthest from the neutral axis, which is pi over 4d square, multiplied by the number of bars in the layer farthest from the neutral axis. This can be translated into the following. We will have to use the equal sign at first whenever we are inserting a formula or an equation into an Excel cell, followed by NOBB times pi with parentheses is the way we define pi in Excel. So you can type capital letters P and I followed by empty parentheses. This is how pi is written in Excel, followed by over 4, then the diameter square. So this is nothing but a translation of this formula here. Note that NOBB and DBB are input parameters in this table here. So the number of bars in the layer farthest from the neutral axis and the diameter of bar in the layer farthest from the neutral axis are input parameters, and therefore they are used to calculate the output parameter, the area of steel reinforcement in the layer farthest from the neutral axis. Same can be done to calculate the area of steel in the second layer, which is nothing but the number of bars in the second layers times pi over 4 d square, where d here is the diameter of bar in the second layer. For the third output parameter, which is the total area of steel reinforcement, please note that we will be using two of the output parameters just calculated in order to obtain the total area of steel. Now, please pay attention to the difference between the first two equations and the third one. When we calculated the area of steel in the layer farthest from the neutral axis, we only depended on two input parameters, which are dBb and NOBB. When we calculated the area of steel on top of the layer farthest from the neutral axis, we actually depended on the input parameters dBt and NOBT. Now, when we are calculating the third parameter, which is the total area of steel, we will be using these two output parameters already calculated in order to calculate the third parameter, which is the total area of steel, because this one here is nothing but the summation of these two. And therefore, some of the output parameters will depend only on input parameters, while other output parameters will depend on input and output parameters. That's why the sequence here is very important. You need to place those that will be calculated first at the beginning so that you will be able to use them later on. In the fourth equation, we have the centroid to the layer farthest from the neutral axis. If we look at the figure here, we can define the centroid to the layer farthest from the neutral axis YB as concrete cover, plus the diameter of stirrup, plus half the diameter in the layer farthest from the neutral axis, which is dBb. And therefore, the centroid to the layer farthest from the neutral axis can be written as the cover plus the diameter of stirrup and half the diameter of the bar in the layer farthest from the neutral axis. I will stop at the fourth parameter, YB, and call it a day for the third session, and hopefully I will see you in the fourth session to come.